Okay, so could I kindly ask you to take your seats? Is the projector running? I'm not sure. Can we switch on the projector? Okay, who has the remote control of the projector? No, it's not that. That's a white thing. Is there any other way how to switch on the projector? Yeah, just a minute. They say it takes a long. No, the remote is here, so we just it was hidden somewhere. Felix, you said 20 seconds? I'm counting.
No, it's longer. It's after you expected it won't work.
I'm very impatient, so and now it's already long after I expected it to start, and it's still not starting. I think it, like Felix always managed. So I think it's immediate. After you touch it, it's immediate. Okay, so let it give a few seconds to. So just very minor organizational remarks. After we finish this last stage. So it will take between 5 and 10 minutes for the organizers to sum up the grades and then prepare for the closing ceremony. We won't make a break before that, otherwise this would take too long. So I'll take notes into my notebook about the grades. Then the score sheets will be collected. The organizers will sum up the grades, etc. While we'll be discussing the grades, so we'll have more time for discussing the grades. But for the jurors, please also do some comments independently on the score sheet, because if you will be asked to justify your grades, you might not have the score sheets available. I don't know if you want, just make a shot on your mobile phone from the score sheet, because the score sheet, while you will be explaining the grades, it will already be collected. Okay, are we ready to start the report? Okay, so it's time for the team from Georgia to take the floor with the problem number 8, please.
Shall I start?
Yes.
So my greetings, my name is Nicholas and I'm a member from Georgia, and today I'm going to be a reporter for the problem number 8, evidential lines. So the problem statement says that we shall place 2 electrodes into water, supply a safe voltage on the electrodes, and use a voltmeter to determine the potential of various locations. After, we shall investigate how the measured potential lines deviate from our expectations for different conditions and different liquids. Let us start with the problem overview. So we'll start with the explanation of the phenomenon. I'll explain the phenomenon by showing you my external setup and explaining the role of the liquid for the problem. After, I'll divide the solution to the problem into 2 parts. The first one will be dedicated to the point electrodes, while the other one to the linear ones. And for both of the parts, we'll write the appropriate theoretical model and compare it with the external data we have. So let us start with the explanation of the phenomenon by showing the external setup. You can see the linear electrodes, the container, and the current source that was used for all the experiments. You can also see the multimeter we used and the graph paper under the container on the slide. The graph paper played a very important role in the problem, since it made us able to measure the coordinate where the potential was investigated. So here you can see the same setup built for the point electrodes. The point electrodes actually consist of balls, metallic balls that are attached to copper wires. And the copper wires are much thinner than the balls. So now let us explain the role of the liquid. In order to do so, we at first did some preliminary experiments. So you can see that we measured the potential without any liquid, and the voltmeter actually gave us 0 volts. And we believe that this is caused by the method by which the multimeter really works. So it needs to have a resistance much larger than that of the investigated conductor. And when we add the liquid to the container, the conductivity of the investigated conductor increases, which makes us able to measure the potential between any 2 points in the liquid. So now let us go to the actual problem and start with the point electrodes. At first, to build some theoretical expectations, we shall write a simple theoretical model. To do so, we first calculated the charges of the electrodes, and we've done this by writing that the difference between the potentials of the 2 balls should be equal to the voltage on the balls. And from this equation, we calculated the induced charges. By using the simple expressions of the potential created by a point charge, we've calculated the distribution of potential in the plane of the electrodes. You can see the qualitative graph for the distribution. So the potential is on the vertical axis, and in order to get the potential lines, we shall equalize the expression to some constant and solve the appropriate equation. You can see both the solution of the equation and the expression on this graph, on this line. So now we shall also explain how we took data from our experiments. So we had one rod of the multimeter attached to a single point in space. Of course, this single point in space played the role of a 0 potential point, while the other rod of the multimeter was buried during the experiment. You can see on this slide the received dependence between the potential and the coordinates, and it is pretty like that we received in the theoretical data. In the theoretical analysis. So now it is also important to explain how we built the potential lines themselves. So you can see on this slide the graph for the dependence between the potential and the y coordinate for a fixed x coordinate. We've had our simulation build the same dependence many times for different fixed x coordinates, as well as for different fixed y coordinates, the dependence between the potential and the x coordinate. So if we want to find the potential line with a potential equal to 4 volts, we shall find as precisely as possible all the points with potential equal to 4 volts. So in order to do so, the simulation actually attach the points to the neighboring points to each other, and then we can also build the horizontal line on 4 volts. The intersection points were the points with a potential equal to 4 volts, found as precisely as we could. So, using this simulation we've got and the theoretical analysis in the theoretical model we've shown you before, we've compared the two to each other, and you can see that there is no agreement between the two. Now we are to explain the disagreement between the theory and the experiment. So we believe that the potential lines should be perpendicular to plastic container. Now I'll explain the reason why. So since the plastic is a much better force conductor than the liquid we've used, I believe that the electric currents should not flow from the liquid to the plastic container, which actually means that the electric field lines should be tangential to the walls of the container near the walls. And this actually means that since the potential is since the electric field is the gradient of the potential lines, this actually means that the potential lines should be perpendicular to the walls of the container. We have this condition that our system has to satisfy, and in order to account for this condition, we use the well-known imaginary charge method. So the imaginary charges help us to account for the electric field created by the induced charges in water. And now you can see that on this slide I've showed you the infinite number of imaginary charges. However, this is just a result of 2 iterations of our simulation that we built, and the actual simulation accounted for 20 of such iterations. So we've got as many charges as we could in order to make the theory as precise as possible. And it is also worth to mention that we have other imaginary charges created by the boundary between the liquid and air, as well as the boundary between the lower layer of the liquid and the container. So this creates another infinite number of imaginary charges along the vertical lines that are on the electrodes, and you will see that we will account for these imaginary charges by assuming that the field created by those charges is the same as the one created by an infinite cylinder. So we have an infinite cylinder, and if you want to calculate its potential, it will be the easiest to just calculate the field created by the cylinder using Gauss theorem, and integrating the field, we can easily get the expression for the potential difference created by the cylinder between any two points in space. And now you can see the comparison between the theory built on the imaginary charges that are such cylinders, and the comparison between this theory and the experiment is very good comparison, since you can see the pretty good agreement between the two. Now let us go to linear electrodes. First, we can see that the experimental graph for the balance between the potential and the coordinates is pretty much like the one we received for the previous model for the point electrodes. If we want to calculate theoretically the field created by those electrodes, we also need to know what is the distribution of charge along these rods. So, in order to calculate the charge distribution, we make the following assumption: that this distribution will be very much like the distribution of point charges that are distributed along this cylinder of a finite and fixed length. So we've written the Newton's second law for each and every one of them. We built an appropriate numerical simulation and solved the equations numerically. So you can see the graphs for the dependence between the ball's coordinate and time, and the equilibrium distribution of the charges, the equilibrium distribution of their coordinates gives us the distribution of charge in the cylinders. As you can see, for all cases, the closest ones to each other appear to be the charges at the bottom and at the top of the cylinders. However, the distances between most of the neighboring ones can be assumed to be the same for all couples of charges, which gives us the result that the charge distribution can be assumed to be homogeneous. We also assume for this theoretical model that the lengths of the cylinders are much larger than the distance between the two, which gave us the opportunity to write that they are semi-infinite. So to calculate the exponential lines created by semi-infinite cylinders in the plane of their foundations will be the same as calculating the exponential lines created by the really infinite cylinders, since the replacement by the system with two cylinders of the semi-infinite sizes will only add the same potential to each and every point, which means that the exponential lines will not be changed. Now you can see that we, using this theoretical model, we've actually calculated the distribution of the potential as a function of coordinates. And by equalizing it to some constant and solving the appropriate equations, we've got the potential lines, which appear to be, these equations appear to be, we managed to solve this equation analytically, and we received circles as potential lines. We've compared these circles to the experimental results. As you can see, again, there is no good coincidence if we don't take into account the imaginary charges. So again, we are to use the same simulation in order to return the imaginary charges to our theory. And finally, you can see the comparison between theoretical and experimental models with the imaginary charges being taken into account as well. And there's some pretty good coincidence between the two. On this slide, you can see that we've changed the distance between the electrodes. The coincidence is again good, however, it is a little bit worse in the very bottom of the container. We believe that this, since the same interference did not, this is very like the systematic error, since all the points are suddenly were into different coordinates, and we believe that this occurred during the experiment itself. That, for example, the graph paper was moving in the reference frame of the container. And now let us finally go to the conclusion. So we built an experimental setup in order to find the distribution of the potential as a function of coordinates. Then we written the theoretical model for point electrodes. electrodes. Actually, we've compared it with the theoretical one. However, there was no good coincidence between the two. We explained this coincidence by the induced charges in the liquid. Now, we will also compare the new theory with imaginary charges to the experimental model and received some pretty good coincidence. We made an assumption in order to find the charge distribution on the linear electrodes. We're using the appropriate theoretical model, and we've got some pretty good coincidence when we take into account the imaginary charges. Thank you for your attention.
Okay, I think
Okay, so am I right when saying that you didn't vary your liquids in your parameter variation at all? Yes
No, I have the parameter variation.
Yes or no?
No,
Did you vary
not
your
the
liquids?
liquids. The form of the electrodes and the distance between them.
Okay, you didn't vary liquids. Okay, that's important. What would you say your main error sources were?
Again?
What were your main error sources?
Error sources. Of course, the error of the multimeter itself and the error of the coordinates measured. These were the two sources taken into consideration with the errors.
Follow-up question: was your measurement device non-invasive? So when you used the second tip of the multimeter meter to measure it, did you move the water, or how did you make sure that it was non-invasive?
You mean the voltmeter?
Yes.
Did it not interfere with the experiment, right?
Okay.
Okay, I believe that, of course, whatever method you choose, you will, of course, interfere with the experiment. However, because of the large resistance of the multimeter, I still believe that the charges induced on its rods will not change much in the experiments.
Okay. So I'm not quite sure if I missed this, but why exactly did you use linear electrodes and did not vary other shapes, for example, like a square electrode or something like that? I think that would be much more interesting than just the linear rod.
I've taken into account, I've also conducted experience for sphere electrodes. I've shown you this.
Yes.
So I believe that two shapes are enough. However,
wouldn't other electrodes be more interesting because you could observe peak effects for those?
okay, what are you meaning by peak
Peak
effect?
effects, like where the potential on the surface of the electrode is higher, because the radius is higher in comparison to the other.
The surface of the electrodes is basically an exponential line itself, so I don't believe that it will be more interesting to do so. It will just change the boundary conditions.
Okay, thank you very much. Sorry, time's up, but you'll still have time to discuss during the discussion. Time for preparation.